I am David Koslicki from Oregon State University. Typically, the kind of research that I do is in metagenomics. This here is a research talk about something else different, something I've been branching into. It has to do with biological networks and computing and finding motifs, or interesting little subnetworks of larger biological networks. So, title of my talk, I'm going to be talking about IndieCut, this algorithm that myself and a couple collaborators developed that evaluates the performance of different motif finding algorithms. So, the basic outline of this talk, first off, I'm not going to assume that everybody here is intimately familiar with what motif discovery algorithms do, so we'll talk about that briefly. Talk about a few different algorithms that people use to try to discover interesting motifs. Then we'll talk about IndieCut, which is a thing that we can use to evaluate their performance, and then talk about a few different results after that. By the way, I want this to be interactive, so don't feel like you have to hold your questions to the very end. If you have any questions that you want to ask, feel free to do so in the middle, and I will attempt to address them. So let's start at the beginning. Motif discovery. What is motif discovery? All has to do with networks, biological networks. So these can be maps of the different interactions of different biological processes. So for example, here is a very small toy example of a regulatory network. We have microRNAs, transcription factors, and genes. And we have arrows drawn between these quantities if they affect the expression level of the target. These can be represented, for instance, like gene regulatory networks, like I said. They can also be protein interaction networks or many other different kinds. For what I'm talking about, it doesn't really matter where you got your biological network, just that we have one of these networks. One very fruitful approach that biologists have taken beforehand is to view that these biological networks right here are sort of like circuit boards. You know, with a little circuit board, you can wire it up in different ways and try to create some sort of device. We can take that same viewpoint for these regulatory networks right here. And so they're built up from smaller components. So for example, right here, if I zoom in, I pull out one little component right here, and this is called a coherent feed-forward loop. So translating what this thing is right here, we have a transcription factor that decreases the transcription rate of this other transcription factor here, which increases the transcription rate or activates this gene right here. And this transcription factor also suppresses that gene right there. And so if you imagine that we put a minus sign on this edge and a plus sign on this edge, the total thing would be negative. And then from here to here, it goes down. It's also negative. So that's why it's called a coherent feed-forward loop. OK, so we got this network. We build it up from smaller components. So you might ask, well, which components are actually interesting or important? Which ones actually serve to be very critical to some biological process that this network, some function that this network is performing? Well, of course, you could do this experimentally. So for example, you could design an experiment that attempts to modify one of these networks and see how that affects the system that you're studying. Unfortunately, this is actually really rather time-consuming and expensive to do. So typically what people do is a computational approach instead. So the computational approach of discovering which one of these motifs is biologically interesting is called motif discovery. So motif discovery. Questions so far? All good? Big picture? Fine? Excellent. Cool. So identifying these surprising subnetworks. So let's go ahead and stick this guy off to the side and stick this motif over here. And this is, I'm going to call it a candidate motif because I don't know if it's biologically interesting or not quite yet. So how do I assess if it's biologically interesting? One thing that I can do is I can generate a whole bunch of random background networks. So I generate a whole bunch of other random networks like this. And I can say, does this motif show up in that network? And if it does, how many times does it show up? So as an example, let's say that this candidate motif shows up 8 times in the first one, 20 times in the second one, and none in the last one, for example. What you could then do is generate a histogram that looks like this, where you have the number of times the motif is observed and the number of random networks that we have sampled here. Then you go back to your original biological network, and you ask yourself, how many times did this motif actually show up in this original network? Well, it showed up like 22 times. Okay. After that point, you calculate a p-value. What's the probability of observing this many or more of this motif in a randomly generated network? So you calculate that p-value right over there. If this p-value is small, then you say, oh, this motif is surprising. For randomly generated networks, I don't see it a whole lot. In my biological network, it's showing up all over the place. This must be a really important component. Like this must be like a capacitor or something if you're taking the circuit board analogy. Fantastic. Well, first question you might ask is, how do you generate these random networks? Well, you can't just do completely arbitrary random networks. It has to preserve some sort of biological realism. Somehow has to be rooted in the original network that you started out with. If you preserve that biological realism, then after that point, it should be uniformly random otherwise. So what sort of biologically realistic properties are we attempting to preserve? Well, those constraints, to be able to say that, I'm first off going to have to break this up into bipartite layers for my particular graph. So as an example, if we take this very simple one, which is just transcription factors and genes, so we have transcription factors and genes right here, I can break it up into two bipartite layers. So let's look at the transcription factor gene layer right here. So all I do is I put all my transcription factors on top, I put all my genes on bottom, and I only include arrows that go from transcription factors to my genes. And so I get something like this. Transcription factor 3 targets gene 2. Yep. Transcription factor 2 targets gene 1. Yep. And this one targets both of my genes. Indeed it does. That is one bipartite layer. Now for the transcription factor targeting transcription factor layer, because notice we have arrows going between that, it becomes just slightly more complicated. We do this. We put a minus sign if the arrow is originating from a transcription factor and a plus sign if it's terminating in a transcription factor. So for example, right here, transcription factor 1, this has two outgoing arrows to other transcription factors. So it goes to transcription factor 3 and transcription factor 2. So we have an arrow here and we have an arrow there. Transcription factor 3 doesn't have any outgoing arrows to any other transcription factors, so it has no arrows like this, and so on. So I've broken my network up into a couple different bipartite layers. Now remember, I'm trying to describe for you the biological constraints that I'm supposed to preserve. That's coming now. What I do is I preserve the degree sequences. That is, I count the number of outgoing or incoming arrows. I'm going to get an integer, and I want to preserve those. So for example, right up here, this has one outgoing arrow, so it has a degree of 1. Also one outgoing arrow, so it's a degree of 1. Outgoing 2 arrows, so it's a degree of 2. 2 and 2, and I can go on and I can keep labeling these things, and I get all my degree sequences. So preserving the biological realism, by the way, I did not come up with this scheme. This is sort of the established way to go about doing it. Biologists think that this is the right way to do it, so I'll believe them. For the rest of this talk, though, I'm only going to consider one single layer. It's going to make the math and the equations a whole lot easier to describe, so I'm just going to concentrate on one layer. Great. Preserve these degree sequences, wire it up randomly otherwise. That is how you generate these random background networks. So, summarizing, what is motif discovery? Given fixed degree sequences that you got from your original biological network after breaking it up into bipartite layers, how do we sample from all such bipartite graphs? I'm going to state this in a slightly different way. It's going to make it a lot easier to think about. I can describe each one of these graphs with a matrix. So let's say for sake of argument, I have an out degree of 1, 1, 2 and an in degree of 2, 2 corresponding to this particular bipartite layer right here. I'm going to represent this thing with a matrix. It's not quite an adjacency matrix and it's not quite an incidence matrix, but it should be pretty clear. Let's take a look at this guy. This transcription factor targets the first gene. So that transcription factor targets that first gene, so I stick a 1. It doesn't target the second gene, so I stick a 0 here. Transcription factor 2 targets gene 2, so I stick a 1 right here. And the third transcription factor targets both genes, and I get this guy right here. So this is a 1-to-1 and onto correspondence. So every time I have a binary matrix like this, I can have a bipartite network and conversely as well. The really handy thing about this is notice what happens if I sum the rows right here. I get 1, 1, 2. Oh, hey. And if I sum the columns, I also get 2, 2 like this. So our degree sequences correspond to the row sums and column sums of this binary matrix representation. Always be representing these things with an R and a C for rows and columns. So putting my motif discovery problem statement a different way, I want to sample from all binary matrices with fixed row and column sums. And that's how I generate these particular binary matrices. Okay. This is how I want to be thinking about the problem for the rest of the time. Whenever you think bipartite network, think matrix. Whenever you see a matrix, think bipartite network. Seriously, no questions so far? Maybe everybody's seen motif discovery before or something? Okay, cool. So how do people actually do this in practice? Well, I'm going to talk about 4 algorithms. Of course, there are many other ones, as you know, with bioinformatics. We're rife with different tools and approaches, right? So I'm just going to give a sampling of the different kinds of motif discovery algorithms that they have. One of the more classic ones is this thing called FAN-MOD, Fast Network Motif Detection. And what it is based on is this concept of edge switching. So with edge switching, here I have that same network. And I can take a couple of the edges, like this edge right here, that edge right there, and I can decide to switch their endpoints. And if I switch their endpoints, boop, now the network looks like this. And you can switch back, or you can switch 2 other ones, etc. And if you keep switching, 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 you end up with what FAN-MOD says is a randomly sampled bipartite network. And notice it also preserves the degree sequences. Because you're taking one of the degrees over here and sticking it here, and taking one of those and sticking it back, so it doesn't actually change anything. Similarly with the binary matrix approach, you're just taking ones and you're just moving them in the binary matrix. So that's one approach to generate these random networks in the background. Como Finder is another edge switching based technique, co-regulatory motif finder. It's basically FAN-MOD with an extra constraint, which says if you've switched 2 of them, don't ever switch them back. So you might imagine that we started out with this guy and we switched the edge, and then the very next step, we could just unswitch them. Como Finder says, well, don't do this. Okay. Some other methods are not based off of edge switching. For instance, diampsis, diaconus Monte Carlo importance sampling. This instead decides to start with a matrix that's all zeros and fill in ones column by column using a weighted importance sampling scheme. Not going to go into details because it's not too important, but just giving you an idea that is not edge switching. It's basically throwing ones in a matrix of all zeros. Another non-edge switching one is war swap, weighted and reverse sampling, swap sampling. Similar to diampsis, except if you might imagine, if you start with all zeros and you start putting in ones, you might eventually get stuck somewhere. For example, right here, if here's my row sums, there's my column sums, I start with all zeros, I decide to start with the middle column and I stick a 1 right here, and then I stick a 1 right there, and then I stick a 1 right here, and oh shoot, I'm stuck. Because I have to stick a 2 right there. That's not a binary matrix, right? So this little reverse swap thing says if you're starting to fill these in column-wise and you get stuck, what you can do is take one of these and one of those and just switch them, like so. And now it's a binary matrix, and you can verify that the row sums and the column sums are exactly what they should be. So these are the basic algorithms. Great. Next thought. So, which one should I use? I actually want to do motif discovery. Which one of these algorithms is better than another one? Some of these come with theoretical guarantees. So for instance, FAN-MOD and to some extent diampsis right here have some sort of theoretical guarantee associated with it. For instance, with FAN-MOD, if you completely sample every single one of those graphs and you keep on running it long and long and long and long enough, it's absolutely guaranteed to be a uniformly random sampling of all such bipartite networks. But does that ever actually happen in practice? Let's try to figure this out. So, how do we do evaluation? Recall, these randomly generated networks should preserve those biological constraints. All of them do. They all preserve the degree sequences. So the main thing is the second one. They have to be uniformly random otherwise. How do we test that? Well, up until now, what people have been doing is considering very small degree sequences like this. Let's say my row sums and column sums are both 1, 1, 2. Then you can sit down and you can figure out that there are 5 possible such bipartite networks. Here they are. Here's 1, 2, 3, 4, 5 of them. I guess I reversed this thing. Instead of 1, 1, 2, it should be 2, 1, 1, where you go from the bottom up, 1, 1, 2. Okay, in any case. There's 5 of them. That's pretty easy. So then you can run any one of these algorithms, like FanMod or Como Finder, a bunch of different times on there, and just generate yourself a histogram, like this. And ask yourself, how close is this to a uniform distribution? And you go to the next algorithm, you do the same thing, next one, do the same thing, next one, do the same thing, compute a few statistics, and you're good to go. Okay, that's great. This does not work whatsoever for larger degree sequences. Why? Well, we have this fantastic theorem right here from the area of enumerative combinatorics, which don't even bother attempting to read it. But what it basically tells us that this little guy right here, this is the number of such binary matrices with fixed row and column sums. And we see here an inequality. So this inequality gives us a way to estimate how many binary matrices exist with fixed degree sequences. I have an upper bound and I have a lower bound. And you can go through and you can compute it. So this is great. So if I have a larger degree sequence, something like this, then I can enumerate or estimate, using this formula right here, the number of different random bipartite networks I have. And it turns out this guy has about 10 to the 8th of them. Ooh, so it's starting to grow pretty quickly. In reality, these degree sequences for real biological networks, they have like 400 or more. These vectors are length 400 or more. If I were to take the same pattern and increase it to a vector of just size 40 instead of 400, I end up with 10 to the 256 such bipartite networks. That's huge. That's beyond astronomical, 10 to the 256. So this approach of just enumerating all of them, running it a bunch, and seeing how close it is to the uniform distribution is never going to work. Because theoretically, you should never ever see a graph, the same graph more than once, for one thing. So there's no way that you're going to be able to exhaustively sample and compare it to a uniform distribution. So what do we do? How do we assess the uniformity of this network sampling on realistically sized graphs? When the sample space, that is the space of all bipartite networks, is way too huge to actually enumerate exhaustively. That is where IndieCut comes in. So this is with a couple of collaborators over at Oregon State, a recently graduated PhD student, and a collaborator, Molly McGraw, over in botany and plant pathology. This is over on bioinformatics. All the fun math, as you might imagine, is in the supplementary material, that fun formula and other stuff like that. But in any case, let's try to get to the main idea. What does IndieCut do? Well, remember the law of large numbers, right? If you have an IID sequence, so an independent identically distributed sequence of random variables, and you take the sample average, that is 1 over n, the sum of those random variables, then if you let the number of samples that you go get bigger and bigger, that sample average is going to converge to the expected value if it's IID. So if we want to test whether these motif discovery algorithms like IndieCut are IID sampling from these bipartite networks, we should expect that the sample average is going to be close to the true average. As a pictorial representation, imagine this is the huge space of all bipartite networks with 10 to the 256 different networks in here. Every little gray dot right here represents an output from one of my algorithms. So I queried it just once and it gave me one random graph. That's one of these gray dots. This E right here, this is the true average of all these networks. Remember, I'm thinking about these things as binary matrices, and so it's pretty clear how to average these things, right? You can just sum them all up and divide by the number. There's no way you're going to be able to do that because there's way too many of them. But in any case, you can also compute the average of the sampled matrices from your algorithms. And then the idea is you want this, not this, not this, right? If you're trying to sample the space uniformly randomly, you want this to be uniformly random. You do not want it to be clustered in some area not around, or the sample average to not be close to the expected value. So the whole idea is we want this quantity right here to be small. We want the distance between the sample average and the true average to be small. That all good? Simply law of large numbers kinds of stuff. If this thing is not big, or sorry, if this thing is not small, then we have good evidence that this is not uniformly randomly sampling my space. Great, very simple idea, hopefully. Two immediate issues. One is, how in the world do we calculate E, right? There's supposed to be 10 to the 256 of these guys. You're not going to be able to compute them all and then add them up. And beyond that, what do I mean by these little vertical bars? What norm am I talking about? Well, you can imagine a bunch of different matrix norms, right? Because this is a matrix. That's a sum of a bunch of matrices, so that's another matrix. So this is some sort of matrix norm. There are a ton of different matrix norms, right? So which one should I be using? Those are the two main issues addressed in IndieCut. As I said, we can't calculate E directly. However, we can compute a proxy. Now, of course, first off, let me back up a second. If you have very pathological degree sequences, you can figure out what E is going to be. So for instance, if your degrees sequences were all ones right there, it's pretty clear what your matrix is going to be. It's going to be 1 over the length of those guys, or 1 over the sum of the lengths. Pretty clear what it's going to be. However, if they're more complicated, there's actually no existing formula to figure out what this thing is. We can compute a proxy. Remember this big old Ghoulies theorem right here? Well, if we concentrate on this part right here, this is a minimization problem. Here we have a product of a whole bunch of different things. The inputs of this functions are vectors. We got vectors right there. This R and that C, those are the actual degree sequence values right here. And so when you minimize this thing, you're minimizing this big product. So if you take the log of this thing, then you're minimizing a sum of things, which just turns out to be a convex problem. So actually computing this little quantity right here is not difficult at all. It's a convex optimization procedure. Great. So you can figure out which couple of vectors minimized this thing right here. Great. So you take the minimizers of those, and then you form this other matrix Z. You take those couple of vectors, you take the I and jth entry, you form the product, and you form this ratio right here, and we get what's referred to as the maximum entropy matrix. Maximum entropy matrix. This thing is not E, but it is going to play the role of a proxy of E. So for all intents and purposes, you can think of it as E, which is why I've also colored it red, right? So we got that part. That's what I'm going to use. I'm going to replace that E right here with a Z instead. We still have one problem. What matrix norm am I going to be using? So that matrix norm is referred to as the cut norm. Who here has heard of the cut norm? Anybody? Cut norm? No? Seriously, nobody? Ooh, 1. Yes, 2. Excellent. OK, good. So this is great. I'm very glad that I actually included an example of the cut norm next. Here's the cut norm. Perfectly clear definition, right? Well, let's step through it real quick. So this is a matrix norm. So this M right here, that's just a matrix. And the way it's defined is through a maximization procedure. These I and these J's right here, these are my rows and columns. So you pick some rows, you pick some columns, you sum your matrix using indices only from those rows and those columns, and then you take the absolute value afterwards. So for an example, real quick, let's say you have a matrix like this, just some matrix that I came up with. You're trying to figure out which rows and columns will give you the biggest sum right here. So for instance, I could pick my rows to be 1 and 3. And I could pick my columns to be, just one column. How about 2 right here? And then you look at where these colors overlap. Right there and right there. You sum those entries, and then you take the absolute value. Sum those entries, take the absolute value, we get 1. And now, I can actually do better than this. You might imagine, what if instead I took all 3 columns like this? Take column 1, take column 2, take column 3 like this. If I were to do that, then summing over only these entries right here, I would get 2. And you can actually sit down with a pencil and paper and figure this all out. This is a small enough example that you could actually exhaustively enumerate all the different rows and columns combinations that you could do, and you'd find that actually 2 is the maximum. This is the biggest that you can do. So the cut norm of this matrix right here is 2. Great. This norm is very famous, actually, in theoretical computer science, because it's very useful for different graph algorithms. For instance, max cut, min cut, things along these lines. That's where its name comes from, actually, because cut norm. But in any case, here's its definition. Great. That's the norm I'm going to be using. So in this problem right here, where we want our sample averages to be close to our true averages, that's going to be our cut norm. So there we go. We addressed those couple of problems. You might ask, why? Right? Why the cut norm? The whole reason is that we can prove that if your algorithm samples networks uniformly or equivalently, if you have an independent and identically distributed sequence of random binary matrices with fixed row and column sums, then this formula right here is true. What is this saying? This is saying with high probability, this quantity is small, right? So with high probability, that quantity is small, which is what we wanted. This right here is basically law of large numbers kind of idea. It's actually more powerful than that. You have a central limit theorem actually with this cut norm and with that maximum entry matrix as well. But in any case, this is our theoretical guarantee that our idea of sample average close to true average works for this maximum entry matrix and that particular norm. All good? Question? Yes, thank you. Yeah. Right, exactly. So take the contrapositive of that statement. So if it's IID, then this thing is small. If that thing is not small, then it's not IID. We wanted our algorithm to be independent and identically distributed, right? We wanted a completely uniformly random sampling of this space, and we wanted them to be independent samples as well. So if we run our particular algorithm and this thing is not small, we have evidence that it is not IID sampling. Yes, thank you. Yeah?
What is small?
What is small, right? Yeah, glossing over a whole bunch of details right here. We have these kappas and n's and things along those lines that I'm not describing right here for sake of time. But one thing that you'll notice right here is that, oh shoot, this is supposed to be red, whoops. But in any case, I'm actually normalizing this by the cut norm of Z as well. So yes, you would imagine that as you change the size of these matrices, what is small right here is going to change quite a bit. However, I'm sort of standardizing this by dividing by that guy. So this epsilon right here is going to be between 0 and 1. Closer to 0, better.
But like, so you're saying like the IID is small, but like is there like a threshold at which you say they are IID or not IID?
Great question. You can get results for saying that for a particular sample size and everything like that, then here's my 95% confidence interval. If it's an IID, then it should be between this and this. You can definitely do that. Yeah. What we are going to be using it for, though, is comparative purposes. So for there, it doesn't really matter how big it is, just which one's bigger. Yeah, great question.
Can I just make sure that I understand this? Mm-hmm.
Which one? E. This, oh, epsilon, yes.
No, I mean the matrix.
Ah, this one, yeah. Yep. But here I'm taking a difference.
But the cut norm would be like, the sum of the elements.
Yes, but here, notice I'm taking a difference. Yep. Yeah, so this one's always non-negative entries, but I'm taking a difference, so it will have negative entries. Yeah, great observation. Last question, Sharon. Yeah. Mm-hmm.
So as it's traversing over graphs,
Yep.
the different graphs output are not independent. So
Bingo.
would that be able to apply this result?
Yes, you will. That observation right there, this is basically saying exactly what you said. The numbers that are going to get spit out from this basically says what you say, as that fan mod is not sampling them independently. Yep. Yeah, so you're jumping ahead of the results section. But yes, that's exactly right. OK, so we're done with the math, right? Not quite, unfortunately. This cut norm here, computing this thing is max SNP hard, which is just another fancy complexity class, which implies NP hardness. It's actually sort of even worse than NP hardness. It's not even approximable, or if it is approximable, then within an arbitrary epsilon amount, then P equals NP. So it's a really hard problem. Computing this norm is a really hard problem. Ugh, that's not good, right? Because we wanted to compute it. Cool thing is I can bound this thing between efficiently computable quantities. What do I mean by that? Here's my cut norm. I can bound it between a couple of different quantities that I actually can compute. Over here on this side, we have this quadratic integer programming problem right here. And on this side, we have this semi-definite optimization problem over on this side. I'm not going to go into details over here a little bit too much, but it's some really cool ideas. This maximization procedure and that maximization procedure look a whole lot similar to each other. We got this m out front, and we got these two little quantities that are either dotted with each other or multiplying with each other. Because I'm maximizing over vectors over here, and I'm maximizing over integers over here, this thing is referred to as a semi-definite relaxation. That's why the little SDR guy right here. This you can compute in polynomial time, which is great. You just pull an off-the-shelf optimization algorithm, in MATLAB or CSDP or whatever package you want. You throw that at this guy, and you get yourself one bound over here. You got yourself a couple of vectors. You get yourself a random hyperplane. You dot these vectors against it. You take the signs of these things. You get a feasible x and y here, and that's going to give you an estimate. Skipping over a whole ton of details right here, because this is not too important to understand these particular quantities. What is important to understand is I can compute this, and I can compute this guy right here. So I can bound this quantity. There's no guarantee about how tight these bounds are going to be. If there was, then P equals NP. So I'm pretty sure that no. But we can compute those couple of guys. Punchline. What is IndieCut? IndieCut is an interval. Top bound and lower bound. And this right here is the bound on the right. And this over here is my bound on the left right there. And I'm guaranteed that this quantity that we wanted small right here lives somewhere in that interval. It lives in this interval. So whole idea is if your network sampling algorithm samples independently, identically distributed uniformly, then this interval will be close to 0. If it doesn't, you have evidence that one of your hypotheses have been violated. Not independent, not identically distributed, etc. All good? Maybe? Excellent. So, in the last 7 minutes or so, let's talk about results. So, on a small toy network like this, a bunch of transcription factors, a bunch of genes over here, I can get a graph that, or a figure that looks like this. Over here, I have my network sampling algorithms. X-axis here, I have that relative cut norm. That is, this interval. I'm plotting intervals right here. So in particular, my left bound is right here, and my right bound is right over there. I know that this cut norm quantity that I'm interested in lies somewhere between these two. And if this interval is closer to 0, it's better. It's more evidence that this network sampling algorithm is IID. If it's bigger, it's worse. So we can see that this edge switching algorithm, FanMod right here, is doing worse than diampsys and WAR-swap on this particular toy network. Como Finder has an asterisk right here because it's right here. So it's rather far out this direction. Como Finder, much bigger relative cut norm. So we can see that these non-edge switching ones are doing better, as we would think, because the way the algorithm is designed, it's not really IID. Question?
Zero still can be non-IID.
Sure. Yep.
So about this, we have no answer about.
Yes, you'd have to be careful about how you state these. You could say that there is more evidence that FanMod is not IID as compared to diampsys. Right. Yes. So you have to be careful how you state it, but general idea is you want the interval that way. Yeah. What about a more realistically sized network? Let's take part of the human regulatory network. Let's focus on one particular layer, the microRNA to gene layer. This has 12,000 nodes. So just imagine how many binary matrices there are when you take the sum of the row and the column sums of the number of entries there, 12,000. It's huge. I give myself another graph that looks like this, or diagrams. Diampsys over here is in red because it just would not run on a graph of this size. It would just segfault out. So it wouldn't run. So I don't get any results for that. We have the same general pattern showing up. Here, Como Finder is at least on our scale somewhere, but it still sort of skews things. What we have is that this interval, by the way, the thickness of these things are too big. I couldn't get Mathematica to make my edges small enough, but these are extremely tight little intervals. So tight that if I were to take the difference between the endpoints, I get something like 10 to the minus fourth. So these are really, really tight little intervals. These edge switching algorithms are doing worse than this non-edge switching algorithm right here. So you might wonder why this is. Do we have some intuition about the performance difference? Why are these edge switching algorithms doing not as well? Remember that spaceable networks that I had, where I had the true average of all those sampled networks and the sample algorithm sample average over here? Well, if you were to use Como Finder, it's basically sampling the space in some sort of Markov fashion. You could imagine some sort of Markov chain sitting over this gigantuous thing right here, where I have uniform equal probability to go to the next graph, where the next graph is defined as one edge switch away. So if I were to run Como Finder for a bit, it might look something like this. It starts walking along, and sort of the next graph is very close in terms of edge switches. It's only one edge switch away to the one just behind it. There's no backtracking, and I couldn't figure out how to get this thing to self-avoid random walk inside a circle. That was a bit gnarly. But in any case, you could imagine that this is basically what Como Finder is doing. This is how it explores the entire sample space. Notice what's happening to our sample average right here. It's wandering away from the true average like this. And it's not ever going to uniformly sample this thing unless I was able to exhaustively sample this thing, which you're not going to be able to. In comparison, one of these non-Markovian ones like WAR-swap, the sort of intuition that you want to have behind is it's sampling it, since the next matrix that I sampled has absolutely no relationship in terms of edge swaps to the previous one, right? Because you start with all zeros, you throw in those ones. Then you start with all zeros again, you throw in some ones, etc. It's basically sampling your space like this. There's no relationship in terms of edge switches between the previously sampled graph and the next sampled graph. And you can see that our sample average and our true average are getting closer and closer together. So now that you've done all this, that might be exceedingly obvious to you now. If you're trying to sample random networks, and your next sampled network, the only difference is one edge swap, that's not really much of a random network, right? So if you're trying to uniformly sample a space that you can't enumerate, don't do it in one of these sort of like Markov-ish fashions. Yeah. Okay. Another cool thing is how much is enough? How many samples do I need to say that I've sampled my space in a good enough fashion? Really interesting thing is every one of these algorithms right here just give this, we saw like 200 is enough, or as much as you have time for, because there's no really way to quantify the performance of these things. Now, you can do this, and you can get figures like this guy. So here again, I have the different algorithms. It's difficult to show the evolution of an interval over time. So this is the upper bound of the cut norm interval, and this is the lower bound of the cut norm interval. And you can see as the number of networks that you sample gets bigger and bigger and bigger, you can see, as you would expect, this thing starts decaying and getting smaller and smaller. The nice thing is if you generate a figure like this, you could figure out how much is enough. How many network samples do I need to be satisfied with the performance of my algorithm? If you saw this diagram, you would say, yeah, you would need at least more than 500, right? Because look at how much the performance improves as you continue outward. This actually turns out to be really important, especially in real networks, because if you don't sample enough, for instance, FanMod recommends a few hundred samples, then if you were to run FanMod for a few hundred samples, look at which motifs are significant in terms of those p-values, and then do it again, and then do it again, you get different answers in each time. Why is that? Because you're not sampling enough of these graphs. If you perform that same experiment where you sample a few thousand of them, and you can tell that you need a few thousand because of this figure right here, then all the ones that are reported as significant are the same run to run. So if you undersample, you can miss out on some motifs or erroneously report ones as significant. So in conclusion, IndieCut, it's the first method to assess the performance of these guys on realistically sized networks, ones that you can't just enumerate them all. Allows you to do some sort of quantitative comparison, at least in a contrapositive fashion, of network sampling uniformity. And it helps the biologists figure out which algorithm they should choose and how long they should run it for. So if you're interested for more info, this is the paper up here. It was also posted in the schedule, that link. All the code to run the entire kit and caboodle is up here on GitHub. If you just want that fun cut norm approximation thing with those couple of minimization procedures, that's also on my GitHub. But there we go, 2 minutes under time. Thanks for your attention. Yeah. Yeah. Great question. So what we did was basically said, well, if you're performing poorly on one layer, your performance cannot improve by tacking on more additional layers, right? So since we're only comparing these algorithms and saying which one's better and which one is worse, then that didn't affect the math, really. The basic idea is most of these algorithms, what they do is they operate layer by layer, and then they just glue the layers together. Yeah, so then it's basically the same idea. What happens on one layer is what's going to happen with other ones. Yeah, great question. Yeah?
Yeah, great talk. I think I agree with your reason to that particular Macaulay, what you said, is an MCMT. But I think just theoretically, for example, from MCMT, you also kind of have theoretical guarantee to get a uniform distribution.
Right.
I think the particular problem you have for that algorithm is this lot of local change is not related to long-range jump. So it's rather a problem of that particular algorithm than in general, the problem of workflow, the problem for MCMT in general. I think just trying to get your opinion on that.
Yeah. So the next steps of what we're doing now is how to optimally design an algorithm to perform this task. Now that we have a way to assess performance quantitatively, we can start thinking about these such things. One sort of naive or initial approach is to, know that your sample average is very close to this maximum entropy matrix. So you can use that as a proxy of the center of the entire space, and you can define jumps in terms of that as well. Yeah, yeah, exactly. Last question. Yeah.
I was just wondering, your way of saying that something is not
Mm-hmm.
what happens instead of just comparing two variables? Because here you have something similar, you have bias that has really low variance.
Mm-hmm.
And I was wondering if your same procedure was run by trying to compare variances between different algorithms, would it still be the same ones as the most performant ones? Or
Yeah, great, great question. So I'd say two things about this. One, no, we did not look at the variance. We're just looking at the means. The reason why that is because the theorem that we had, I stated it in terms of just the expectations. To do the same whole thing that I just did, and you'd know when the big variance is big enough, that kind of thing, you'd have to go back to that theorem and rework it so that you could figure out what the variances are. But that wouldn't stop you from just looking at the variance, trying to figure out which is the right variance to be talking about. Because remember, I'm talking about cut norms here. So how do I quantify the variance in that terms? But yeah, you could definitely do that. Because you're right. You could pick an algorithm that is maximum entry matrix and just return that to me every single time almost, and just shifting it away to a binary matrix. That would be very interesting. None of these algorithms actually do that, but you're right. You have to be careful about that. Cool. Excellent. Okay, Sergey, who's running this session? I could just answer questions all day.
I want to take a break.
Okay, we'll take the break. Cool, thanks.